Welcome everyone. Today we're going to be talking about the dot product. So when we talk about vectors, when we think back to the knowledge that we have of geometric vectors, we did some operations with those vectors that were like addition of those vectors, subtraction, and we did do a multiplication, but this was simply a multiplication with a scalar and a vector. So we weren't really multiplying two vectors together. Now, we still don't technically do a straight multiplication of vectors, but there are some operations that we can do with vectors where we use products. And one of these is the dot product. So basically what this is finding the product of the magnitude of one vector with the magnitude of the other vector that is in the same direction as our first vector. So essentially, what we want to think of is kind of like a projection of one vector onto another, and that little component that is in the direction of the other vector is going to kind of be a product. So here's what I want you to imagine. We've got two vectors over to the right here, and if we imagine some sun rays kind of shining down on this vector almost, basically we're going to have a shadow that is projected at a 90-degree angle, right? The sun rays are going to kind of stop here and the shadow will get projected down. And this shadow is going to be projected down onto vector B. And so we're going to have a little component of this vector A that actually goes in the direction of vector B. And this is what we call the part of A that kind of shines onto B or goes in the same direction as vector B. And we call this the projection of vector A onto vector B. So you can kind of see this over to the left here. We say the dot product of A dot B is the magnitude of vector B multiplied with the magnitude of the piece of A that is going in the same direction as B. So this is kind of like rectangular vector components. So we're going to notice here that if we use the angle theta between vector A and vector B, that this is the adjacent side, and our vector A, or the magnitude of vector A, can kind of be like our hypotenuse. So if we arranged with cos theta, what adjacent over hypotenuse would be in this triangle. Okay, I'm looking at this right triangle right here. Then basically what I'm doing is I'm doing the magnitude of the projection of A onto B, which is the adjacent side, over the magnitude of vector A, which is the hypotenuse. And then rearranging, if I multiply this magnitude piece right here up onto the other side, we get that the projection of A onto B is actually the magnitude of A times the cos of A. So if I simply take this piece right here and sub this in, we actually get this formula for the dot product. So A dot B is what we say is equal to the magnitude of A times the magnitude of B times the cos of the angle between the two vectors. And what that will allow me to do is actually find the product of this magnitude times the magnitude of the entire vector B that is in the same direction there. So that's the idea. So here's our formula. We just saw it above, but A dot B is equal to the magnitude of A times the magnitude of B, times the cos of the angle between the vectors. And remember, we always refer to the angle theta between the vectors as the angle when the vectors are arranged tail to tail. Okay, so our vectors can be, this angle theta, they can be anywhere between 0 and 180 degrees. And the other important thing to know about the dot product is that it actually gives us a result that is scalar. So when we do the dot of two vectors, we actually get out a scalar answer from this. And that's because we're basically looking at the product of their magnitudes and not the product. We can't really actually multiply two vectors together. So if we're just doing the product of two magnitudes, we just get out a scalar component. All right, couple properties of the dot product. So we can actually tell if two vectors are perpendicular to one another if the dot product of those vectors equals 0. And that basically means, like, if I have two vectors that are perpendicular to one another or at a right angle, there's really no components of those vectors that go in the same direction as one another. So if we imagine kind of like those light rays shining down, as I said above, if this is vector B, let's say, and this is vector A, there's no component of vector B that is going in the horizontal direction that A is going in. So we can see here that there's actually no product between the projection of B and A that go in the same direction, so the dot product would be 0. There's also a commutative property, which means that it doesn't matter which order I do the dot product in. I can do A dot B or B dot A, or if you want to use U and V, that's fine. And it will give you the same answer. Also, there's a little property that says if I dot a vector with itself, the result will actually be the magnitude of that single vector scaled or squared. And we can also multiply the dot product of two vectors by a scalar. And it doesn't matter the order that I do this in. So this is an associative property, which basically means I can multiply a scalar in by one of the vectors and then dot them. I can dot them and then multiply the scalar, or I can multiply the scalar by the other vector and then dot them, and I'll still get the same answer for all of them. Okay, and then let's say I had three vectors, u, v, w. This is kind of like a distributive property, and it says that if I do u dot v plus w, it's actually equal to u dot v plus u dot w. Okay, so we are going to use our formula to determine the dot product of each of these vectors here. So remember, grab your calculator, work along with us, and remember that we want to be in degree mode. So here A dot B is going to be equal to the magnitude of A times the magnitude of B times the cos of the angle between them. So this is going to be 20 times 30 times the cos of 40 degrees. So let's enter this together in our calculators. And you should find out that you get about 459.63 here. Okay, and remember, this isn't a vector quantity, this is actually a scalar quantity. So it just kind of shows us the result of how these vectors work together. Okay, so here is an example of what I was just talking about in the properties here. If I wanted to do m dot n, again, it doesn't matter the order in which I do this. I'm going to do the magnitude of m times the magnitude of n times the cos of the angle between them. I'll leave this as a formula for now. And we can actually clearly see from our diagram here that the angle between the vectors is 90 degrees. So if you want to enter this into your calculator, you can, but I know already that the cos of 90 is actually 0, so that's going to make the product of all of this equal to 0. And then finally, this one has an obtuse angle rather than an acute angle. So if you imagine here that there are sun rays kind of shining down on this vector, and it's trying to shine in the direction of vector v, these are actually going to shine down. This is actually going to shine down in a direction that is opposite to vector v. So u and v are actually acting in opposite directions here. So if this is our little projection of u onto v, I should expect that if these are working in opposite directions, we actually get an answer here that is negative. So let's try it out. So v dot u, and do the magnitude of those two things times the cos of the angle between them. Okay, and when I do the cosine of an angle over 90 degrees, you have to remember that the 90 to 180 quadrant cosine is actually negative in this quadrant. So it should make sense that we get a resulting answer that's actually negative here. Okay, so negative 4,250. Okay, so that brings us to a little summary. So what we've just seen above is that in our examples, the dot product can be positive, negative, or zero. And we can actually predict whether it will be each of these things based on the angle of theta. So if theta is less than 90 degrees, we will get a resulting positive answer. If theta is greater than 90 degrees, we will get a resulting negative answer from our dot product. And if it's equal to 90, we're going to get an answer of 0 because there's no components that are working in the direction of the other vector. So what we just saw were some examples of geometric vectors and how we can do the dot product of those vectors. But we've also just learned about Cartesian vectors or algebraic vectors. And these are vectors that are expressed in component form that we can actually plot on a Cartesian plane. So when we do the dot product of these, we want to see how much we kind of want to see how the x's are working together for both the vectors and how the y's are working together for both the vectors. So basically, you're going to multiply the x components together, multiply the y components together, and you're going to add them. So let's take a look at example 2a. We want to find u dot v. So I'm basically just going to take the x components here and multiply them, and then we're going to take the y components and multiply them, and then we'll add. So we're going to get 20 minus 21. That will give us negative 1. Okay, that gives me some indication that these vectors are kind of making an angle together that is greater than 90 because the result is negative. Okay, let's take a look at this one. Okay, so multiply the x's together, multiply the y's together, we get 2. Find a vector that is perpendicular to vector 6, negative 11. So we know from above that if one vector is perpendicular to the other vector, then they create a dot product of 0. So there are many vectors that we could represent with 6, negative 11 that would actually be perpendicular because if I have 6, negative 11, say I have this vector, I guess it would be going in this direction. Okay, I can have many different vectors. I can have one here. I can have another one this way. I can have a longer one this way. So there's infinite different vectors that we can actually show that are, sorry, I didn't draw that very well, be in the same direction. There's infinite vectors here that are infinite different lengths that we can create that would dot with 6, negative 11. There's a little trick that we can use in order to generate one of these vectors. And the little trick is this. Swap the x and y and change one of their signs. It doesn't matter which one you do. So for instance, if I switch 6 and negative 11, and let's say I make 11 positive, you can do a little check here. They have to dot to 0. So if I do 6 times 11 plus 6 times negative 11, this gives me a dot product of 0. Okay, so this could be one potential answer, 6, negative 11, 6. And another potential answer, if I swap them, let's say, and I make 6 negative, that will also dot to 0. So this could be another option. Or if you can think of any combination of things that could multiply to 6 and to negative 11, and then their sums would be 0, any of those things could work. But I think this is probably the easiest little trick that you can do to create a vector that in fact is perpendicular. Okay, and then finally, we're going to take a look at an application of the dot product. So you may recognize some of this from physics, but you may not have known where the formula came from. So in order to calculate mechanical work, you can actually basically take a look at the product of the magnitude of the displacement traveled by an object and the magnitude of the force applied in the direction of that motion. So usually we use the units Newton meters, and this can be also called joules. So let's take a look at an example here. Let's say Max is pulling a golf cart up a hill with a force of 120 newtons at an angle of 20 degrees to the surface of the hill. This hill is 100 meters long. Find the work that Max performs. All right, so I've taken a second just to draw a really basic diagram here. We have a certain displacement and a force. The force is at an angle of 20 degrees to the hill, so I've kind of tried to angle it as if we're kind of traveling up a hill here. And we know that the force is 120 newtons, so we can fill that out in our diagram here. And we know that the displacement is 100 meters. And that's why when we do the dot product of these two things, we get Newton meters, because they're kind of in different units of measurement. So here's a little formula for you guys. Work is going to be equal to force dotted with the displacement. And that means, using our dot product formula, that it's going to be the magnitude of the force times the magnitude of the displacement times the cos of the angle between those two vectors. So work is going to end up being 120 newtons times 100 meters times the cos of 20 degrees. So if you're following along with your calculator here, let's try to enter that in to see what we get. And I'm going to say let's round to about 2 decimal places here. So I'm getting 11,276.31 Newton meters. Okay, we can also express this as joules, but we're going to do another application later that also uses the measurement of joules. So I like to kind of differentiate work and that later application by using Newton meters for work and joules for our later application. So I'm going to keep this guy, I'm going to keep this guy as Newton meters. But if you put joules, that's fine as well. All right, thanks for tuning in today.